Hi, my name is Sachs. I'm an application engineer on our HPC applications performance team. And today I want to talk to you about our new ARM-based Graviton2 instances and how you can use those for your HPC workloads. So in this talk, I basically want to answer three questions. What is Graviton2? What is ParallelCluster and how can I use that for HPC jobs? And how do I run my HPC jobs on a cluster in the cloud? So let's get right into the first question. At reInvent 2018, AWS launched their first ever ARM-powered instances powered by the Graviton processor. These featured the ARM Neoverse cores and contained up to 16 cores and 32 gigabytes of RAMs per instance. These were our first ever ARM processors and are built on top of the AWS Nitro system, which offloads many of the traditional virtualization functions to dedicated hardware. This hardware offload delivers practically all the compute and memory resources of the host to your instances for better performance and better security. So these instances delivered a significant cost savings over general purpose instances for any kind of scale out workloads, such as web servers, containerized microservices, data or log processing, and everything else that can run on a small core, small memory footprint. So basically not HPC, not the main HPC workload. In December of last year at reInvent, we announced our second generation instance powered by the ARM processor. The Graviton2 delivered a major leap in performance and capabilities over that first generation processor. They provide up to 40% better price performance over comparable current generation x86 based instances for a wide variety of workloads. And they are now available in three different types with 2, 4, and 8 gigabytes of RAM per core, respectively. These instances contain up to 64 cores, are enhanced networking enabled, and have higher storage throughput than their predecessors. Now, how do you use those actually for HPC? The Graviton2 based instances are available for our HPC tools like ParallelCluster or AWS Batch. These tools are used to create a familiar environment for HPC users and leverage cloud resources for the compute and storage needs. So compute resources only get provisioned when jobs are placed into the queue and are quickly scaled down when the cluster is idle. This means basically your cluster will at most be a head node. And every time you submit a job, you will actually have compute nodes, but only as for the time as this job is running. Another major differentiator of the cloud is that not only can you make your compute resources be ideal for your application on a per application basis, but you can do this with all kinds of auxiliary stuff. So network or storage needs. So whether or not you need a big parallel file system like a Lustre or object store or just some fast local storage, you can mix and match all of that into your cluster. So let's take ParallelCluster as an example. ParallelCluster is built out entirely out of AWS services. The whole cluster is managed as infrastructure as code in CloudFormation. This allows you to update and adapt any aspect of that cluster by changing text-based configuration files. Actually, the whole code of ParallelCluster is hosted on GitHub. The compute fleet will grow and shrink on demand as you submit jobs and as they complete. You can choose to either submit jobs to AWS Batch, which is our own scheduler, or use the autoscaling capabilities of EC2 to adapt the cluster size to your scheduler's needs. New compute instances can automatically signal the head instance when they are online, and this is done by managed non-blocking signals to ensure the delivery of the messages. And finally, identity and access management allows you to control not only the access to the cluster, but also limit the resources that the users on the clusters can actually use. And all the configurations, as well as the required machine images, are stored in S3 for low latency access from basically anywhere. So once you have selected the instance type and all the auxiliary stuff like networking and storage, all the hardware that makes up your cluster, you can mix and match that with different operating systems. In this case, it's Amazon Linux or Ubuntu. Typical HPC job schedulers, you could use Slurm or Torque, or as I said before, AWS Batch, and pre-installed software components. So OpenMPI, which is automatically EFA enabled, and that's our low latency kernel bypass fabric, or nice DCV for remote visualization. While those compute resources will grow and shrink based on the demand of your jobs and your application, you are still in full control over all resources that are being allocated. So you can take control of that over command line interface, a web console, or all kinds of different SDKs. And you also have the possibility to take full control over performance monitoring. If, for example, you've built a Grafana dashboard before, you will want to have stuff in there like CPU metrics, memory usage, I/O, and network counters. You can have these things and have them automatically grow and shrink as your compute fleet shrinks. So here's an example of something that a friend of mine has built on top of ParallelCluster, where you can have all those different metrics on an instance level. You can have metrics on the parallel file system. You can even have some logs, what's going on the machine right now, or have an eye on the budget. How much resources did you actually spend this month? So this is a basic example showing you stuff like CPU usage, but you can go all the way down to looking at TLB misses, last level cache usage, all of that. And there are examples out there on GitHub on how to do those things. So this is an example using Grafana. You can build anything else using your own solution, or you can, for example, use our managed CloudWatch service. That's our native metrics collection and dashboarding service, anything you like. Additionally, there's also a Cost Explorer dashboard that will show you your current spending details and what you're spending on. So I'd like to invite you to try this out on your own. Go to HPC workshops and start building your own HPC cluster in the cloud. This website gives you a step-by-step, self-paced workshop to stand up your first cloud HPC cluster and run applications on it. You can select any of the Graviton2 based instance types that I mentioned earlier, and add parallel file system, remote visualization, and anything more, and use your different schedulers. You can upload your applications and workflows and start building your apps on Graviton2. Thanks for your attention. If you have any feedback or questions, please reach out to me via my email. Bye.